It's located halfway between Munich and Stuttgart in the southern part of Germany. And this is apparently the location where I come from. And it's for tourists, it's well known for basically three things. The first is that in the caves around Ulm, they discovered already decades ago, and the archaeologists are still working on this, the first man-made sculptures that we know about. So these pieces were actually carved out of ivory, mammoth ivory, actually 40,000 years ago, when the first modern humans arrived from the Balkans and they settled in these caves. This is an amazing piece of art, and I always say this is basically the basis of what we are doing here at the university. Because the society somehow gives us the freedom to think about everything we want to think about. And at that time, where hunting was essential to survive, they set someone aside to actually carve this piece out of mammoth ivory, which took weeks, presumably. And it's a piece of imagination. It's not something that you can find, because it's a combination of a lion head, apparently, and a human being. So, and then there's a cathedral, which is from the Middle Ages, and it's actually the highest cathedral in the world still. Yeah. So, but that's of course not what I wanted to tell you. That the most important thing is this guy, because he was born in Ulm. Yeah. The family actually came from a village next to Ulm. There is still Einstein family living there. And this is important for what I'm going to talk about, because in 1905, as you all know, there is this miraculous year where he published a number of papers, and one of them, which eventually brought him the Nobel Prize, was about this thing, a heuristic viewpoint concerning the production and transformation of light. It's a photoelectric effect. So it's the interaction of light and matter at that time are electrons, and they are basically spitted out of a metallic material by shining light on this. And Einstein found the right way to describe this, and he did this in terms of light quanta that were called photons. And so at this point, he was the first to really deal with the two entities that are already included in my questions, namely electric charge quanta and photons. And then, of course, as you know, time went on, quantum mechanics was developed, and electromagnetism and say material science in a way were combined in quantum electrodynamics, which is the foundation of everything that, apart from the large colliders we experience in our labs, and it describes the interaction of electrons via the exchange of photons, and it does so with the dimensionless quantity. That's the fine structure constant, which is actually a combination of constants of nature, and it describes how strongly the electromagnetic field and the charge quanta, the fermions, are interacting with each other. Now, as coming from condensed matter physics, I would express it this way. This is the vacuum impedance. The vacuum impedance is basically mu naught times the velocity of light divided by the resistance quantum, and the resistance quantum is h divided by 4e squared. So it's impedance divided by, and this is, as you see, it's due to the fact that the velocity of light is finite. And this quantity is small. It's very small. Yeah, it's approximately 1 over 137, and this is good because the stability of everything that's around us depends on the size of this fine structure constant. Now, can we do experiments with quantum electrodynamics in the, say, non-relativistic regime? Yes, of course we do. People have done this, and here is a nice example. Now you can see the reference. The reference is Arroche, I have to tell you. So these are nice experiments where people put atoms, and atoms contain electrons, in cavities so that they can interact with light field. And the typical dimensionless coupling constant between the light field and the electron is given by the fine structure constants, power 3.5, divided by a dimensionless volume. So when you shrink basically the volume of the cavity, this dimensionless quantity increases. And so when you also take into account that the lifetime of photons in this cavity is sufficiently long so that the number of traversals of an individual photon forth and back in the cavity is very large, then the effective constant with which you can basically interact here, atoms and light field, which is a product of this dimensionless quantity times this number of transfer of passovers, is much bigger than 1. So whenever in each individual event there is very weak coupling between the electron, between the atom and the photons, but because the photon travel forth and back many times, because they are somehow encapsulated in the cavity, you can see everything that in the non-relativistic sector was predicted by quantum electrodynamics. The first thing you do is the exchange of energy quanta. So absorption of energy and then relaxation of the atom in a coherent manner. This is Rabi oscillations. And the next thing you can do is the lamp shift. The lamp shift is a renormalization of the transition frequency within the atom by the vacuum fluctuations of the electromagnetic field on the cavity. Yeah. And nicely be seen, and for this you need exactly to have this condition. These are impressive experiments, one has to say, and of course they brought Horst the Nobel Prize. Yeah. But the charge that I was referring to in my question is still bound to the atom. It's not something that can freely move. And to do this, to see freely moving charges, we have to leave this field of cavity quantum electrodynamics, and we have to think about how to realize similar experiments in condensed matter physics. Because in condensed matter systems, the electrons, as we all know, are freely moving. We can manipulate them by applying voltages or electric fields. And these fields, magnetic field, electric field, directly related to current and voltage, and those play the same role as positional momentum in quantum mechanics. And we can do so by having, for example, this AC circuit. There is an inductance, there is a capacitance. You basically write down, as you have done in the lectures. And then when temperature is actually sufficiently low, namely much lower than the typical level spacing that you expect from this harmonic oscillator, then you see the quantization of those levels. And this was not something which was obvious. It was something that came only clear in the 1980s, that these electrical circuits can actually be used as test beds for quantum mechanical phenomena. It's not clear. You know? So here is a nice example of what one can do with charges. This is actually an island. There is 2 contacts here. There is some voltage here. There's some voltage here, and charges can be actually brought one by one from here to here to here. Yeah? And this is just to demonstrate that people are now able to not only control, say, light in the way I have shown you, but also that they can control individual charge quanta to an extent that they can actually relate the current to the frequency with which you here tune the gate voltage. And then the proportionality is simply given by the electronic charge and then some integer which tells you about the number of charges that within one period you basically transfer. There is also a conductance quantum. This is what people discovered in the last decades. So there is some finite conductance, which is related to the inverse, of course, of the quantum resistance. So there's some wavy nature of the electrons basically make this constriction, for example, where electron waves come from here and go through here to make this with a finite conductance. Okay. So now we can more precisely go back to the question, can we see the quantum tunneling of electric charges? So this is just a cartoon of what I have shown before, 2 metallic leads, and then there is some constriction, and the electron waves are supposed to tunnel through. And when there is an electric field applied or a voltage applied, these charges are accelerated, and so they radiate. So when I'm talking about C, the quantum tunneling, then I'm talking about the radiation that is related to this transport of charges across this constriction. Question is, can we see it? General answer, no. Why? Because you have an energy continuum of charges. They come with very, very broad frequency spectrum, and typically they radiate, but the radiation is immediately absorbed in the bulk. The bulk is a continuum, and it's basically almost impossible to see, to basically detect those electromagnetic responses. So we somehow have to deal with things that people in quantum optics, when it came to cavity quantum electrodynamics, have done as well. They used cavities, they placed atoms in cavities in order to engineer somehow the spectral density and to make this way the interaction between the atom and the electromagnetic field of the cavity as strong as possible. So we have to be smart to somehow engineer our system such as to observe this radiation. And one way to do so, and this is what I'm going to tell you in the next few minutes, that this can be done basically by design of the density of states, first, and second by, again, using a resonator. Density of states means that we use a superconductor. And we use as a tunnel junction a Josephson junction. So this was an element that was basically theoretically, one has to say, predicted by Brian Josephson. Briefly after BCS theory for superconductivity was formulated, no one believed the poor guy. He was a PhD student at that time. Yeah? But then shortly after people were able to actually fabricate this, he won the Nobel Prize at a very early age, 10 years later. And then, as some of you may know, he somehow developed strange ideas, because he somehow left the basis of serious physics. He diffused away, exactly. So, and this is an energy diagram of what's going on in this Josephson junction. Two metallic leads, and they are separated by a tunnel barrier, by an oxide, basically. And what Josephson predicted is that the charge quanta which carry the current in a superconductor, and those are Cooper pairs. These are pairs consisting of electrons with opposite spins, and they basically bound together. This way, they become bosons, and then they can basically condense in a superconducting fluid, and this gives rise to this vanishing resistance. So the Cooper pairs can actually tunnel. The tunneling current depends on the difference of the phases of left and right superconducting fluidum. So this is a Josephson phase, and the current is proportional to the sign of this phase. Okay, so there is a current even though there is no voltage. So the system tries to somehow cope with the fact that on left and right side there is not the same phases, and it somehow wants to regulate this and to exchange the phases, and it does so by sending Cooper pairs from left to right or from right to left. When you apply a voltage, then there is a time-dependent phase actually, and then the IV curve looks like this. You have basically at 0 voltage, you have the superconducting peak here, and then there is nothing happening, because when you look at the energy diagram, this is the Fermi level, this is the quasi-particle continuum, and because this gap here makes the superconducting fluid robust against any immediate excitations, you have basically no current flowing when you apply a voltage, as long as you are below the gap energy. And once you approach this, then there is quasi-particle tunneling. This is the physics of a Josephson junction. Now, to let you briefly tell why the energy scales that are relevant here, which are quite different from what people typically do in quantum optics. So this is a quantum optical regime. You have energies on the order of electron volts. This is what you know from the binding energies of atoms, for example. The typical wavelengths are on the order of microns. For superconducting elements, energy scales are orders of magnitude smaller. So we are talking about microelectron volts. We are talking about wavelength of centimeter, which means we are talking about microwaves. Yeah? So microwaves, this is in gigahertz frequencies. This is a typical scale of those circuits. And here is a nice example of such a circuit. So this is basically two of those Josephson junctions are here. There's an island in between, and then there is some meandering stuff, and this meandering stuff is actually a resonator for those microwaves. And this piece here is the building block of all superconducting quantum computing devices that are currently existing. They are based on this kind of thing. I won't go into the details, but would also mention from the more fundamental side that was in the mid-80s actually, that Tony Leggett posed also a question. Yeah? And the question was, is the Schrödinger equation valid on a macroscopic scales? So you may wonder, why is this? We believe that the Schrödinger equation as the basic equation for quantum mechanics applies to everything. But his reasoning was, well, the Schrödinger equation, of course, it is an effective description of nature because we know that quantum electrodynamics is more fundamental. So could it well be that there is a certain scale, complexity of system, complexity of nature, where the Schrödinger equation does no longer apply? Yeah. And he suggested at this time to use superconducting circuits as test bed for those generic quantum phenomena. Why superconducting circuits? Because the superconducting state is an almost macroscopic wave function. The superconducting fluid consists of zillions of electrons that are bound to Cooper pairs. So it's not a single body, but a many-body wave function, macroscopic wave function, which can be described by a phase and an amplitude. Yeah. So this was his idea. And now let's come to this. Was just a little excursion to tell you that that there was a very fundamental question behind everything that I'm going to tell you now. It started when Pino and Elisabetta and I were still, say, students. Yeah? But this was a fascinating time when there was a new field, basically, that opened for quantum physics. Now, let's come back to the tunneling of Cooper pairs across the Josephson junction. And let's assume that, so this is a symbol for a Josephson junction, this cross with an EJ, which tells you about the energy with which the two superconducting fluids actually interacting, the overlap basically of the two wave functions. This is how it is, what it is. Assume that there is some resonator. The resonator in simple terms is a harmonic oscillator. And now assume that you apply a voltage. Voltage means that you shift the Fermi levels by an energy amount of 2 eV, 2 because Cooper pairs consist of 2 electron charges. So when a Cooper pair tunnels from left to right in this situation, it does so with an excess energy of 2 eV. And you immediately see in this picture that there is no way that the Cooper pair can tunnel because there is no density of states. Typically, we don't see this because the energy, the excess energy is immediately absorbed by the continuum. But now people were able to design their circuits in a way that the only way for the Cooper pair to get rid of this excess energy is to deposit it in this harmonic oscillator. So when the excess energy 2 eV is equal to the transition frequency in the oscillator, Cooper pair transfer is possible, and otherwise it isn't. So it's a resonance condition, which tells you about the frequency, which is related to this voltage, has to be multiples of the transition frequency in the resonator. Whenever a Cooper pair is tunneling, it produces an excitation in the resonator. From the resonator, it can, for example, decay. Yeah? So this is the simple idea. And in a way, this idea already existed 30 years ago. But no one actually thought of looking at those at those photons, yeah, that are spitted out from each of those tunneling events. This only happened to be about 10 years ago, and it happened in the lab in Paris, where most of mesoscopic physics experiments were invented 20, 30 years ago. And so what they did is they not only measured the current, but they also measured the photons that were spitted out, the microwave photons from the resonator. And I want you to first look at the red line. The red line here tells you that there is basically no, forget about this one, there is basically no current. Yeah, there is some bias current here, but basically no current. And when you hit some voltage, you get a peak in the current, in the tunneling basically of the Cooper pairs, and then it basically decays. There is something little occurring here as well. I will come to this point in a second. When you simultaneously monitor the radiation from the cavity, then you see nothing. And exactly at the point where the tunneling current sets in, you find a maximum in the photon current, that the microwave current, the microwave radiation that is spitted out of the cavity, and then it decays. And so this is exactly the type of picture that is confirmed experimentally. Each Cooper pair current is related to the creation of a photon. The photon leaves the cavity before the next Cooper pair arrives. And so there is one-to-one correspondence, single Cooper pair transfer, and single photon emission. There is also something here, which is actually, as you may see, twice the voltage that appears here. And this is related to the production of two photons, because the Cooper pair energy is high enough that you can basically climb up the ladder in the harmonic oscillator. So this was for us a starting point to develop a theory which went far beyond what is done here. And we first did so when we developed this theory to do a Gedanken experiment. So we wanted to understand the physics behind this. And this is, in a nutshell, is provided here in this cartoon. Here you see the cavity levels, the levels of the resonator, equidistant spacing, ground state, first excited state, and so on. When a Cooper pair arrives, it gives its excess energy in resonance to the resonator, and from there it decays. The resonator decays it, and a photon is spitted out. And this, of course, requires that the rate with which the Cooper pairs are transferred is sufficiently smaller than the lifetime, the inverse lifetime of the photons in the cavity. Yeah. Now, what happens when you somehow open the transparency of the junction so that the tunneling events come in a larger frequency, basically, so the tunneling rate increases? Then, of course, the Cooper pair that is waiting for a transfer sees already that there is some photons in the cavity. It will produce another photon, so that basically you climb up the ladder. But at the same time, the junction could also absorb a photon from the cavity, and this energy is, of course, equal to the excess energy, so it can induce Cooper pair back transfer. Yeah. So what you learn from this is that once they are in a regime away from this timescale separation, Cooper pair transfer and lifetime of photons in the cavity, there is a very complicated feedback between Cooper pair transfer and electromagnetic field in the cavity, which means that somehow the cavity field, the electromagnetic field in the cavity, the photons in the cavity, and the Cooper pairs become intermingled to build up one quantum state. Yeah? And this is exactly something that we wanted to play with. This is a strong feedback, and it turns out that it not only requires that you have, say, transparent junction, but at the same time, very strong, Pino and Elisabetta would say, ultra strong coupling between the electromagnetic field and the Cooper pairs. So when we started this about 10 years ago, we didn't know what we basically triggered, because as a result of these first experiments and the theoretical framework, um, uh, the whole field basically developed, and was at one point termed quantum optics of quantum conductors. And this is interesting because for decades, quantum optics developed basically on its own, and mesoscopic physics or condensed matter physics dealt with quantum conductors and didn't care about quantum optics. And so in this field, for the first time, quantum optics and condensed matter physics merged to see quantum phenomena, to study quantum phenomena from different perspectives, from the charge perspective and from the perspective of photons. And so this was not only done with superconducting platforms, it was also done with semiconductor platforms. And when for the superconducting platforms, we termed it Josephson photonics. This is what it is. And there is a number of questions. This is just a cartoon of the design, which is extremely simple. You have a battery, you have a DC voltage, you have a Josephson junction, and you have a resonator. And this is basically everything that you need in order to understand the physics. And there's lots of questions that come with this about the light production, about the dressing of Cooper pairs, so the basically intermingling Cooper pairs with electromagnetic field in the cavity. Is there something like quantum phase transition, and so on and so on. I will now first very, very briefly, on a very, say, fundamental level, develop the theoretical basis for this, and then I will show you a few nice examples how by engineering the circuitries one can basically engineer the radiation that is spitted out of those resonators. So first about the theory. This is again a cartoon that you know. This is a Josephson junction. There is a Josephson coupling energy. This is the resonator, and you write down the Hamiltonian. This is basically the Hamiltonian, the quantum version of an harmonic oscillator, which is related to this AC circuit. And this is the Hamiltonian of the Josephson junction. There's a cosine phi here. In the current, there's a sine phi. In the Hamiltonian, there's a cosine phi, because the current is basically the derivative of the Hamiltonian. And these two entities are connected or included in a circuit with a DC voltage, and so Kirchhoff rules apply, so that the total voltage, which is imposed from the outside, is actually be dropped at this point or at this point. So the total voltage is basically the voltage at the junction and the voltage at the resonator. And because the voltage at the Josephson junction is related to the phase, as we know, one finds a very, very nice relation. The Josephson phase cannot move freely and independent of what's going on here, but it is imposed basically by the external voltage plus the phase that drops at the resonator. And this phase at the resonator is nothing else than the position of the harmonic oscillator. And the position of the harmonic oscillator can be expressed in A and A dagger, as we all know. And then there is some prefactor, and the prefactor tells us about the 0-point fluctuations. So this is what it is. Yeah? And the 0-point fluctuations for such an LC circuit are simply the ratio of the impedance of the resonator divided by the quantum resistance. And this rings some bells, because it's basically very similar to the definition of the fine structure constant. It is, in fact, the fine structure constant for this circuit. Because what we are doing here effectively is we are exploring quantum electrodynamics in a non-relativistic regime, of course, in a specific material, which is given by aluminum and all the materials that basically built the circuitry. Yeah. So this is basically why it's very natural that there is an effective coupling. And this also tells you that because everything here depends on the impedance of the resonator, but by playing with the impedance, we can also play with the fine structure constant. The fine structure constant is not given by its vacuum value, but by playing with the circuitry, by playing with the ingredients in the circuitry, we can actually design the effective coupling between the matter which in this case is Cooper pairs, and the electromagnetic field in the resonator. So this was a Hamiltonian, and then you say apply the machinery that people know very well in quantum optics. Yeah? So the first thing you do, you go to a p photon close to resonance. So for basically p excitation for a given voltage. And then you basically get rid of all the fast oscillating terms, or the counter-returning terms, or the time-dependent terms are basically assumed to be negligible. And what you arrive at is something which is a time-independent Hamiltonian. This is, as you see here, this is a time-dependent Hamiltonian. This is a time-independent Hamiltonian. And I will basically briefly go through to explain you how it appears. So first of all, here what you see is what remains from the harmonic oscillator. It's the detuning basically between the oscillator frequency and the frequency which is imposed by the external voltage. Yeah? So that's very natural. Then you have these p's. Here's EJ, which tells you, well, this is what is reminiscent of this piece here. So everything that appears here is now in the rotating frame close to resonance is basically given by this expression. And you see that there is a dagger to the power of p, which implies that there is p photons are produced for each Cooper pair event close to the pth resonance. Yeah? Because of this condition, the phase of the Josephson junction is no longer freely moving, but it's basically can be replaced by this expression, and then you find that this is a physics. Yeah, Cooper pairs transferred and p photons are produced. This is this guy. The whole thing is decorated by this strange function, which is a Bessel function. It's a pth order Bessel function. Now, why a Bessel function? Yeah? So everyone who knows about driven quantum systems knows that there is a Bessel function has to appear. You know this from the quantum mechanics course, of course, that when you exponentiate cosine or sine, you can basically express it in the sum of Bessel function. This appears here as well, and it's a pth Bessel function, which with an argument which contains the population in the resonator, and then there is here the coupling constants occurring. There is also the EJ, the energy, the coupling energy, but it's not the bare coupling energy. It's a sort of renormalized coupling energy, and it's renormalized by the quantum fluctuations in the resonator. So this is a sort of lamp shift, which appears here, not in the sense that there is a transition frequency, but there is a renormalization of the coupling in the Josephson junction, which already tells you that these are not completely independent entities, but due to the quantum fluctuations, they are tightly bound together. In order to describe the physics of this, we also need to include losses of the cavity, and this is done in a very, very simplistic way. It's done a la Lindblad. Some of you know what Lindblad is. It just tells us it assigns a certain width to these levels so that they are damped, and then there's photons spitted out. Now let's briefly just look at what happens to the current, to the Cooper pair current, when we play with the Josephson energy. Now you may wonder, how do you play with the Josephson energy? I mean, you have two materials. Aluminum is typically taken, and you somehow in the fab you put them, and then immediately it oxidizes, and you put another layer of metal on top of this, and then that's it. And there is no way that you can play with EJ. Yeah. The people, of course, in mesoscopic physics knew how to solve the problem, because they do not use a simple Josephson junction. They take two of them and actually put them in a ring, and what you then end up with is a superconducting interference device, a squid. And in a squid behaves effectively as a Josephson junction, but with the Josephson energy, the magnitude of which can be tuned by an external magnetic field. So this allows you to effectively open and close the Josephson junction. Okay, so this is why to consider the Cooper pair current as a function of EJ is not something which we do only in theory. This is something that people do experimentally. And of course, there is a current because we are very close to resonance. At this here, it's basically the first resonance. So Cooper pair transfer, individual Cooper pair transfer produces exactly one photon in the cavity. And this is what's shown here. So when you open the Josephson junction, then Cooper pairs start to flow. And when you open further, the current grows. This is what you would expect. But at one point, it basically saturates. So this does not go on forever. There is some saturation here. And the question is, why is this? One could already have an idea when one goes back. Just looking at this expression, one would think, well, for p equal 1, the current is growing, but there is this Bessel function, and the Bessel function is actually a nonlinear function, depending on the population in the cavity, and it is this nonlinearity which actually induces this saturation of the Cooper pair current. Yeah? So the Cooper pair current is limited by the feedback of the electromagnetic field in the cavity onto the Cooper pair transfer, because I was already telling you that not only the Josephson junction can deposit energy into the cavity, but when there is an electromagnetic field in the cavity, the junction can also absorb energy. So there's a subtle, say, feedback between Cooper pair transfer and excitation and relaxation in the cavity, and this at one point then leads to this saturation of the current. How does it look like in the resonator? Well, when we are in that regime here, the resonator field, it is finite. Yeah? So this is a Wigner distribution of the electromagnetic field in the cavity. You see that it's at a finite value. So it's a blob. It's a coherent, almost a coherent state, finite number of photons in the cavity. That's all fine. Now, when we look at this point here, close to where actually saturation is set in, then the cavity field looks like this. So it splits. We had a blob, and this blob splits. Yeah? It's actually a phase transition. Yeah? Not a phase transition in the thermodynamic sense, but it is a transition from a situation where one has one blob to a situation where one has a bistability in the system, two of those blobs. And in principle, when we include quantum fluctuations, one can actually switch from here to there. So there is all ingredients that one needs for a quantum phase transition: critical slowing down, there's slow fluctuations which actually connect those. You see it's not completely disjunct here. There is some bridge that connects these two blobs. There is critical exponent for this to occur. So this is indicating that there is a quantum phase transition which appears in these systems, and one can study this by looking at the resonator field. A is the creation of the annihilation operator of the inner space. So it's a quadrature space for all for those of you that this is quadrature space. It's electromagnetic. It's the real and the imaginary part of the electromagnetic field basically here in this. Yeah. Okay, this is in the resonator. But we do not look into the resonator. The only thing that we can observe is what is spitted out of the resonator. Yeah? And this is something which I will now elaborate a little bit on this, and this is work that we have done together with the experimentalists. And the very first thing was whether it is possible to do this Cooper pair transfer engineer in a way that the photons that are spitted out of the cavity do not, say, come out in a Poissonian fashion, so basically statistically independent, but they somehow appear as say, entities which avoid each other. This is something that bosons, and photons are bosons, typically don't want to do. Yeah? They come in bunches or according to Poissonian statistics, but to behave like fermions, this is something what they don't like. The quantity in quantum optics which tells people about the nature of light is the so-called G2 function. The G2 function tells you about the intensity correlation in light. And one can classify this, so anti-bunching is occurring whenever the G2 function is smaller than 1, and bunching, so photons come in clump, basically, when G2 is bigger than 1, and when it's 1, this is how it's actually defined. It's Poissonian statistics, yeah? So they come basically in a Poissonian fashion. Now, what one finds for this particular system that I'm talking about is that the G2 function at 0 delay between the intensities is for weak driving proportional to 1 minus the fine structure constant divided by half squared. Which means when you can play with the fine structure constant to be close to 2, that the G2 function goes to 0, which means that the photons that are spitted out have the tendency to avoid each other and behave sort of fermionic-like. Yeah? And this is what's shown here. So this is experimental results. The condition to see this is, of course, to have a sufficiently large fine structure constant. A sufficiently large fine structure constant means to have a sufficiently large impedance. A sufficiently large impedance of the resonator can be fabricated by having a large inductance. Yeah, so you need a large coil. And this is what is shown here. So this is actually a huge coil, which has a large inductance, which implies a large impedance. And this, in turn, implies a large effective coupling constant. The Josephson junction is placed here. Yeah? And people had to build a bridge, basically, from the inner part of the coil to the junction in order to get the coupling to the Josephson junction right. So what you see here is, as a function of the delay, how the G2 basically drops. It does not drop to 0 because alpha is not exactly 2. It's only about 1, which is still much larger than the vacuum QED value, but it's substantially reduced. And people in quantum optics, whenever the G2 function is below 1/2, they are talking about anti-bunched photons. Yeah. So here we see anti-bunched photons. We also see a very strong reduction of the bare Josephson energy, so this sort of lamp shift kind of effect. The expected value was something like 3 microelectron volts, and it was suppressed to be about 1.8 microelectron volts. The good thing about this is that this bunching effect produces these anti-bunched photons with a very high luminosity, because the Q factor of the resonator is very low. And so they are spitted out in about 10 to the power of 8 photons per second. But as I said, these photons come well separated. Yeah? They don't like each other in a way. Once you have played with a single cavity, you immediately think about 2 cavities. So, for example, you can now use or then use a resonance condition where the excess energy of an individual Cooper pair matches the excitation energies in the individual cavities. This is actually what is shown here. So here's voltage, here's the frequency in the resonator. Here you see excitation of only resonator A. Here you see excitation only of resonator B. And this is where both resonators are excited at the same time by the same Cooper pair tunneling event. And now you can immediately imagine, because both photons, which are spatially located at different cavities, originate from the same Cooper pair transfer, that they are somehow correlated quantum mechanically, or in a more elaborate language, that they are entangled. Yeah? So the next goal was to prove this, and I won't do this in detail, because it takes too long. I want to tell you that there is an entanglement witness typically that one needs in order to prove entanglement. And here the entanglement witness is a specific form of G2 function. And whenever this G2 function is above another G2 function, which is the pink stuff here, then you have entanglement in the two photon. So this is a sort of Henry-Brown twist type of experiment that is done in this two cavity setting, and it tells you that depending on the population in the cavity, there is nice entanglement seen for the photons, microwave photons that are spitted out. And the more photons you have in the cavity, the smaller the degree of entanglement of the radiated photons. Okay, so now we have a single photon source for microwave photons. We have a source for entangled microwave photons. The last thing I'm going to show is a source which produces multiple photons spitted out at once. And this is experimental results which are shown here. So you basically play with the voltage. You hit, say, the first resonance, and as expected, there is microwave photons spitted out. You go to twice this value, which is 2 photon resonance, and great, you see a peak in the photon emission. You go to 3 times, and again, you see a resonance. You go to 4 times, 5, 6, and so on. Now you may think, well, this is pretty obvious. Yeah, this is exactly what I told you. This is pretty simple. The point is that when you estimate very naively in a perturbative fashion the probability in terms of a rate that this appears, then you find that the rate that you have a p photon resonance is proportional to the p-th power of the fine structure constant. Okay, when you now think about the vacuum value of the fine structure constants, and you take the power of 5 or 6 with this value, then you arrive basically as a negligible probability or likelihood that you find that you basically excite those multiple resonances. What people in quantum optics do, they use lasers. Because when you look, I mean, this is technically speaking the so-called Purcell rate, and the Purcell rate is also proportional to the intensity of the light. And when you use X-ray lasers, the intensity is extremely strong, and you can overcome basically the smallness of this of the fine structure constant. This is not required here, yeah, because we can play with the fine structure constant. We can engineer it such that it takes values on the order of 1. Then, of course, the whole description in terms of Purcell rate breaks down, but nevertheless, then this is why we can actually see, and now you understand what I mean when I'm talking seeing something, then we can actually monitor the radiation that is related to the transfer of a single Cooper pair. And to see that this actually behaves as expected, one again uses statistical physics, and one characterizes the nature by using what's called a Fano factor. The Fano factor is defined that it takes the noise power, actually the photon current noise power, divided by the mean photon current. And this can be technically expressed based on the G2 function. I mean, I don't want to elaborate on this in detail, only saying that experimentally one measures the G2 function, as I have shown you before, and from the G2 function one can calculate the Fano factor. And in the regime where the transparency of the junction is very low, one expects, and this is how the Fano factor is defined, that the Fano factor exactly is equal to the resonance condition that I showed earlier. So in that regime, for p equal 1, this Fano factor should be 1, 2, 3, 4, and this is, I mean, this box somehow masks what is shown what is seen experimentally, but it's exactly what happens here. So this is very, very nicely matches the theoretical expectation. When you increase the transparency of the junction and this feedback between electromagnetic field in the cavity and the Josephson junction sets in, then the physics becomes more intricate, becomes nonlinear, and then the Fano factor makes these nice curves, and we can describe this theoretically very, very well. This is how actually the cavity field looks like when you go to the resonator and look how the cavity field looks like. There is actually, for p photon transfer, there's a symmetry in the Hamiltonian, which is related basically to this phase factor. And it's a p-fold theory, a p-fold symmetry, which appears in the cavity. So for p equal 1, we have this. For p equal 2, it's this. For p equal 3, it's a 2 pi over 3 symmetry, and so on and so on. Here you can no longer resolve this, but basically this is 2 pi over 6 symmetry. So there is an interesting pattern of the electromagnetic field which appears in the cavity, and the only thing, the echo of this pattern in phase space, we basically see as radiated photons according to this Fano factor. And with this, I'm at the end. Yeah. I tried to convince you that combining condensed matter physics and quantum optics is definitely something which is interesting. That this platform, these superconducting circuits, allow to tune the QED fine structure constant, so the light-matter interaction, which opens completely new domains of physics. That something similar to phase transitions appears in those systems and can be studied in those systems. And physically, this is related to the dressing of Cooper pairs, to the strong interaction of Cooper pairs and electromagnetic fields, strong feedback effects, that one can use these platforms technologically to produce quantum microwaves, anti-bunch microwaves, entangled microwaves, multiple photon emission from those cavities. What I have not talked about is quantum synchronization, because this is something which appears and is to some extent required in these for these circuits to actually see this phase-based structure, because there is also some low-frequency noise which typically blurs them, and in order to stabilize this, one has to embark on quantum synchronization. I won't talk about this. I can maybe discuss in the discussion. I can mention something, but with this, I'm almost at the end. I also will show you a few people who were involved in this. So from the Ulm side, there is a few of them on the pictures, but some of them have left already, have passed their PhD. From the French side, there is Daniel and Denis. The pioneer of this was Fabien, who unfortunately passed away 4 years ago at a very young age. Yeah. And with this, I'm at the very end, and I thank you for your patience, and open for any questions. Yeah. Okay. So just to make clear why quantum synchronization appears, the point is that I assumed that the DC voltage which comes from the source is ideal, so it does not fluctuate. Yeah? This is difficult because a DC voltage has no phase reference. It's much simpler for an AC voltage. And in fact, any kind of resistor which naturally appears in the circuit makes the voltage to slowly drift forth and back. Yeah? So there is low frequency voltage noise in the structure here. And this voltage noise means that the Josephson frequency, the omega j, moves diffusively, which means that the resonance condition changes in time on a very long time scale, but it changes. And this means that basically when you start initially from something which is well localized in phase space, and then you look how things develop when Cooper pair current sets in, you first arrive at a blob, but then this blob, because of the diffusive behavior of the voltage is then turns into a ring structure. So all phase-based structures are basically blurred by the noise. Yeah? And this is what one has to fight against. And one way to do so is to induce a phase reference signal, which is a very, very weak AC signal in the cavity, yeah, to stabilize this. But when you think about what's the physics now, then the physics is not only the phase that drops across the Josephson junction and across the cavity. There is also the phase across the resistor, the phase that is related to these fluctuations here. Yeah, and so now there has to be, say, a balance between the external field, that AC drive, and the system has to autonomously find the right phase balance between the cavity phase and the phase which drops across this resistance. And you see, you add a little very small, well-stabilized AC drive to the voltage, and then when you look at the emission spectrum, you find that when the amplitude of this AC drive is finite, you get a very, very, very narrow peak. And this narrow peak is what people in laser physics know very well. This is injection locking in technical terms. And for this system, it means that there is that one works with a synchronized oscillator. And the synchronized oscillator is something where the phase is not fixed by the external signal as for a damped harmonic oscillator, but it's something which is actually has its own dynamics. So when you perturb this, the phase does not return basically, but takes a finite value here. So there is some dynamics in the phase that drops across the resistor and the phase that's in the cavity. So these two phases have to be synchronized, and they are synchronized by the external AC signal. And one can, I mean, this is other equation and so on. This is interesting, very interesting physics. Exactly. So in a way, it's a sort of dephasing that is induced by the noise. Yeah. I mean, you see, when I present this to quantum opticians, they think about this picture here that I showed at the very beginning. Here, that we have Cooper pair transfer. They consider this as level inversion. Yeah, because you basically go from an excited state to a sort of ground state. Yeah, I mean it's via transfer of Cooper pairs, but this is what happens. So there is in some sense what we are doing here is a sort of a lasing mechanism, and this is exactly what this guy here. Where is it? I had this slide where all these. Where was it? Copenhagen showed a few years ago demonstration of an AC Josephson junction laser. It's exactly what this idea that he used, yeah, to get coherent light out of this, say, level inversion. So a cavity driven by an DC biased Josephson junction, and what comes out, you drive by DC, but what comes out is AC microwaves, yeah, because they have finite frequency. They are the frequency of the cavity.
I have two questions, but I first will make the preliminary one. How do you measure the photon emitted? Is it
good question? It's
And then there is the second.
You basically, from the resonator, you have a bias T, yeah? And there is the zero frequency stuff is the DC emission, and everything that goes to the AC branch is the microwaves that, the AC microwaves that are related to the emission. This is how they do this experimentally. It's much simpler than we think of it in theory.
So it is not a decay in a transmission line or
no, it's basically it's a line, and the AC current that comes out of this line is related exactly. It's the same line. Yeah.
But then I mean the second question is that may I use this effect as a source of entangled photons, of more than one entangled photon?
In principle, yes. Yeah. So when in this two cavity setup, as I said, what comes out is entangled photons, and in order to prove this entanglement, they basically had this. They measured say correlations from each cavity individually, and then the cross correlations in the Hanbury-Brown twist kind of manner. And this proved that there is entangled photons, and so in principle you can now use these photons. They are specially separated, different lines, and you can feed them into some other quantum device and to play some games, boson sampling or whatever you want to do.
Let's say if I can 2.5 questions. The 2.5 is that if I think two of these devices, can I connect them with the photons emitted, just having a directional photon emission,
okay.
having communication?
That's actually a good point. So I have two of these Josephson photonics devices, and then no, that's sure you can. Yeah, we haven't done this experimentally, but in principle you can, sure. And then drive basically. I mean, you see, we have when it comes to synchronization, you can play these games. Yeah, so I have two of these devices, and then they synchronize each other. One synchronizes the others. It's like coupled pendula, and they exchange periodically energy, and this is how they synchronized.
I'm sorry for the 2.5 questions, guys. So
that's all fine.
so thank you again, Joachim.
Thank you.